Matias is a student of mine, and also Mauro Copelli. In Recife, she's doing actually the PhD degree in Brazil, and she came here to stay one year, working in topics related to anticipated synchronization. And if we are lucky, we are doing an agreement with the University of Pernambuco to have a double degree for her. That means she would be doctor from the University of Pernambuco and the University of the Balearic Islands. So if it works, it would be great because she spent 1 year here and the rest of the time there, and then she will have, in principle, the 2 PhD diploma. So since you know, she will tell us what she has been doing during this year. So thank you very much, Fernanda.
So good afternoon, everybody. Thank you, Manuel and Rosa, for the opportunity to give the talk. I'd like to talk about some results in anticipated synchronization that are part of my PhD. First, I want to show you our collaborators. Claudio, that's my advisor here. Mauro Copelli, that is my advisor in Brazil. And he also spent a few weeks here, I think 5 years ago, working with Claudio. Pedro Carelli, that is also in Recife and collaborated with us. And Leonardo Rolo, that finished his PhD here last year and is now in Australia. So, I want to talk a little bit about what is anticipated synchronization. For those who doesn't know here, I think a lot of you work with that, but I will give a brief introduction, and then I will show our results of anticipated synchronization in neuronal population, in neuronal models, and then extend the results to neuronal population, large scale networks, and then I will show to you how can anticipated synchronization in neuronal population can explain some experimental results of LFP measures in the cortex of macaque monkeys. And then, if I have time, I will talk about what I'm doing now, that it's putting together anticipated synchronization and learning rules, spike time independent learning rules, and see that these results are very similar to experimental results in the weight distribution of the synapses. But okay, let's go. For those who are not familiar, what is anticipated synchronization? So, imagine if we have two identical and non-autonomous dynamical systems, and they are coupled unidirectional in a master-slave configuration, and also, besides the master signal, the slave receives a negative delayed self-feedback. So this system could be described by this set of equations, like they are identical, master and slave, but the slave also receives information from the master and a negative self-delayed feedback. So if we have a system described by this set of equations, this is a trivial solution of the system. This means that y of t is equal to x of t plus td. So the slave in a time t has a state that the master will have in a time t plus td. If we substitute here, we can see that this cancels, and it's a trivial solution, and this is a stable solution. So, this system is verified to be stable in a variety of theoretical and experimental setups, and really study in biological systems is still missing. So, already in 2000, was when proposed the anticipated synchronization, has proposed that this kind of anticipated synchronization can play a role in biological systems and especially in information process in the brain. But until now, this is not very clear. So, the first verification of anticipated synchronization in neural models was done here in 2003, and in papers after that with Cizak and a group of professors here, and they show that two identical Fitzhugh-Nagumo neural models coupled in a master-slave configuration can also exhibit anticipated synchronization if the slave sends a delayed feedback to itself. So, the point here is that even if we have autonomous systems, so even if the master and slave receive an external current, this anticipation synchronization happens. So even if the external current is constant or periodic or even a white noise, they have that the slave can predict the master. So the point here is that to do experiments, biological experiments, this delayed feedback is not, there is no a good biological correlate. So what we propose is to substitute the self-feedback for an inhibitory loop, a dynamical inhibitory loop mediated by interneuron and chemical synapses. So we want to show that for this motif that has a biological plausible appeal, the anticipation synchronization can happen. But now we don't have the self-feedback here anymore, but we have another differential equation that describes the interneuron. And we want to see, it's not exactly a solution of the system, but we want to investigate if numerically these can appear anticipated synchronization. So our model, for who do not know a lot of neural models, we have 3 Hodgkin-Huxley neural models, each one described by 4 differential equations. The first one for the membrane potential, that's going to be the important parameter for us, and 3 others for the gating variables connected to the dynamics of the ionic channels. And in the membrane potential equations are the influence of the external currents, so the synapses and the external current that we can put in our neurons. So if we couple them in the master-slave configuration, now we can use chemical synapse mediated by alpha and GABA that has another differential equation to describe them and enter here in the equation. So we have also an external current that make each neuron alone oscillate periodically, so they have spikes with a period that depend on the external current. And we connect them of excitatory current from the master to the slave, another excitatory synapse from the slave to the interneuron, and an inhibitory synapse from the interneuron to the slave, closing the loop. That's going to be the important thing for us here. So here we are interested in the synaptic conductance of the synapses, that are the strength of the synapse, you can think about that. And changing these conductors can change the regime of the system, as I'm going to show you. So if we start just with the master and slave, if we forget the interneuron, but the inhibitory conductance 0, we have just master-slave coupling, and we have that no matter what are the initial conditions, if we wait a transient time, the system go to a phase locking regime with a well-defined phase difference. So we can calculate the time delay between a spike of the master and a spike of the slave. That's going to be constant in all periods. So if we have just master and slave, we're going to have a regime that's intuitive. We're going to have master spike, then slave, then master slave, then master slave. Okay, this is the presynaptic neuron send a signal, and after that the postsynaptic neuron do a spike. But we can also see that if we turn on the inhibitory conductance, we can have a counterintuitive regime in which, again, no matter what are the initial conditions, the system evolved to a phase locking, but now we have in each period that the slave spike after the master. So slave, master, slave, master, slave, master. And again, we can measure this time difference here. Now, by the definition, this time difference is going to be negative, and we can differentiate both regimes as the anticipated synchronization, in which the time delay is negative, and delayed synchronization regime, in which the time delay is positive. Okay, you can think, oh, this is periodic, and we are just make a so big delay that now you can think that this is negative. Okay, but I'm trying to convince you that this is a local phenomenon, because if you have the time delay as a function of the inhibitory conductance, we start, for the case, just master-slave in a delayed synchronization, so master-slave, master-slave. And if we start to increase the inhibitory conductance here, we have that this time delay decrease. So the master and slave start to spike closer until they reach a zero-leg synchronization here. And if we continuously increase, the slave will spike before the master. So we can think, okay, we can continue increasing that until this slave is so far from this master that he is close to this master. But if we try to continuously increasing the inhibitory conductance, the system loses his phase locking regime. So the system goes to a phase drift regime in which the slave has a high frequency from the master. So we cannot define any more time delay that's constant, because in all periods we're gonna have a different time delay. Okay? So we can, I come here all the time. We can do scanning all the parameters, like looking for other values of the inhibitory conductance and the excitatory conductance from the master to the slave. And we see that we have a large region in which we have delayed synchronization, anticipated synchronization, and the phase drift regime. So in all these parameters, we have a smooth and continuous transition from delayed synchronization to anticipated synchronization.
I'm sorry, GA and GG, are they intensity decouplings, or are they related to delays? Are there specific delays?
No, there is no delay in this model. It's the conductance, it's the amplitude of the input current. You can think
so
like that.
S, which unit is this?
What?
If you go back to the slide before, what is NS? The unit on the x-axis? Nanosieverns.
It's just because the model is quite biological and we try to use a receipt.
Yes.
Okay, we want to see if the model is robust. We can try a lot of things. We can change the parameters, the external currents, the rate of the decay of the synapse, or we can also change the motifs. In all the cases, we have this big region, red region of anticipation, and a blue region, and a continuous transition. So we try a chain of slave interneuron in which each slave is master for the next slave, similar to what people did here with just master and slave. We can replace the constant current by a fourth neuron that we call driver, because he sends synapses from the three neurons at the same time, thinking that these synapses are these currents that it is sending. It's not exactly the same to the three neurons, because there is a dependence of the postsynaptic membrane potential here. But they are quite similar, and there is a similar regime that I showed before. We can also replace the constant current by a colored noise. So if you have a constant current that is light oscillates, we have not very periodical solution, but we still have master before the slave or slave before the master. And we can also use modified Hodgkin-Huxley neural models, using, for example, another types of currents. I did for slow sodium current, and it's robust, and this can happen. So, okay.
When you have a chain like that, like the one that you show on top, I guess that you can tune some of the elements to be anticipated and other ones to be delayed, or all of them do the same?
Yes, depending on the inhibitory conductance here, I can say to this slave anticipated this master, but this slave is after the... But I didn't try too much, but yes.
In principle, you could tune each of them independently.
Yes. So, the possibility of change the self-feedback that we have in the beginning by this dynamical inhibitory loop makes open a new avenue in the exploration of anticipation in biological systems, because this is more common. So we have a proposal to an experiment. It should do an experiment similar to this one did by a group in France that we call the hybrid setup, because they patch clamp a neuron, a real neuron, in vitro or in culture, and they simulate the other two neurons. And it's very similar to what we have here, the master here, the model, and with a computer as a retina neuron. And they send a synapse to this real neuron. And the response of this real neuron, they send to another computer that simulates an inhibitory neuron and send back inhibitory synapse to the real neuron. So in this paper, they were not exploring exactly anticipation, but they did exactly what we want to do, that is changing this inhibitory synapse here. I asked for the data, we are waiting, but we also have a collaborator that wants to do an experiment like that. The point is that we're going to change the model of the retina here to be more similar to this talon cortical neuron, because for our purpose, it's better that the master and slave are as similar as possible. Maybe it could appear anticipation here, but it's not exactly the same of our model. Okay, now we are talking of measure anticipation in vitro in culture, but not really in the brain, because our model is just for few neurons. If we will want to thinking about experiments in the brain, in behavior animals, or even in human, we can extend the model to large populations, and this is what I did here. We replace each neuron by a population of hundreds of neurons, and they are again coupled in a master-slave interneuron configuration. So the first population sends excitatory synapses to the second population, that send excitatory synapse to a third population, and receive inhibitory synapse from this third population, that's the interneuron. The details of the model is that we now do not use Hodgkin-Huxley neurons, but I did some simulations and the results are the same. We use busy cavity neural models for simulate each neuron here. In the master, we have 8% of excitatory, 20% of inhibitory neurons, following a recipe for cortical-like populations. And in the slave, we have just excitatory neurons, and in the interneuron, just inhibitory neurons. In such a way that we can consider the slave and the interneuron together as a larger population, as I'm going to show to you after. But start to this is similar to the other case, so I will show the results like with this motif, because here we can add neuronal variability, so we can make that not all neurons are doing the same, because we know that in the cortex they have different behaviors. We can add noise, so each neuron receives pulse input, an independent pulse input, so the behavior of each population we're going to see it's not periodically, it's periodic, it's an oscillation, but around the mean. And again, the important factors here are the conductance, the synaptic conductance from master to the slave and from the interneuron to the slave. So, looking for the Hasse plots of each population, we can see that they oscillate. So this is the master population in both regimes. We have almost all neurons are spiking here, and then after a period or something, a mean period. And the same for the slave, and the same for the interneuron. But if we pay attention, you can see that the darker region here of the master is happening right before the darker regions in the slave. But in this situation, we have the opposite. So we believe okay, this is an indicator that something like anticipation is happening here. How can we investigate better? We look to the mean membrane potential of each population, so all the neurons, what they are doing. And this is similar to local field potential measures that people do in experiments with multi-electrodes. And we can see that the peak of oscillation happens, of the master happens before the slave in one situation, and the peak of the slave population happens before the peak of the master in the other situation. So we can define a mean period and a mean time delay, because now the difference here changing each period, but for a lot of parameters they are very robust, so we can take a mean and the square roots. And in this case, they are oscillating with a frequency around 7.7 Hertz. We can also take the Fourier transformer here to look the frequency and look to the period. So again, we have that changing the inhibitory conductance, we change this time delay or this mean time delay here with the standard variation. And similar to the other case, we have that if we increase the inhibition, the delayed synchronization regime undergo to anticipated synchronization regime, but the system now is more robust, and we will not go to a phase drift regime anymore, but the system come back to a delayed synchronized regime if we increase a lot this inhibition, the inhibition. So here, for very small values of the conductance, we can have B stability or phase drift if they are 0. But as is a small part of the region, I'm not going to show the results, but we can measure them with return map or stuff like that. So we have the same kind of measure if you change the oscillatory conductance here from the master to the slave. The time delay again has a smooth transition. Here it is near zero-leg synchronization if we want to study better this region. And we have another way we can look to the phase diagram of the oscillatory inhibitory conductance, and again we have a big region of anticipation. These lines are the graphs that I showed to you that maintain constant the inhibition and just changing the excitation, and we have smooth transitions here. Or we can also measure cross correlation and histogram. So if we want to have another measure of anticipation, we can calculate the coherence or the cross correlation of the LFP curves, and you can see that for delayed synchronized regimes, the peak is positive, the peak of the correlation is positive here, and for anticipated synchronized regimes, the peak of the cross correlation is negative. So considering communication through coherence hypothesis in the brain, is good that a given structural motif give flexible patterns of coherence. So for flexible communication, so these motifs can show not only because of the anticipation, it's important, but both because we can have the two behaviors here. So we can look to locally to neurons and not to the population. So we can look to histogram of the probability density. If you take a pair of pre and postsynaptic neuron that the presynaptic is in the master and the postsynaptic is in the slave, we can measure all the time delay between each spike of this neuron and do an histogram for all the pairs of neurons in this situation, and we can again see the signature of the anticipation here, because the peak in anticipated case is going to be negative and the peak in delayed synchronization is going to be positive. This means that if you take two pairs, pre and postsynaptic pairs of master and slave, and compare in a delayed synchronization and anticipated synchronization, maybe you cannot say in which regime they are, but if you take a lot of pairs, you can do a statistic. So here we have that a master and a slave, then a master. So it's quite anticipating this one, and the other ones are delayed. But in the anticipation regime, you have both situations, the slave master and master slave. So it's not triggered to say just looking for one pair of neurons, if you just can catch two neurons. So our model is also robust for more noise. So if you increase the pulsar input that each neuron receives, the oscillation frequency is going to change. We tried for higher frequency, 15 Hertz, and the diagram is quite similar. And we also try to this modified topology that I tried to say to you before, that we can put together slave and interneuron as just a similar population to the master. And this is better for compared to experimental results, because if you are measuring with electrodes in different cortical areas, we will not distinguish from oscillatory and inhibitory neurons. So you're going to put an electrode here and see all the signal here. So we did this different motif, and we have a similar diagram. So it seems that is robust the result, even if we consider oscillatory and inhibitory together. And then we're going to use these results to compare with the experiment. In 2004, Brovel et al. Show a lot of LFP measures of multi-electrode neurons in different brain, in different cortical areas of macaque monkeys, doing some go and non-go tests that the monkey has to press a keyboard or not, depending on the target in the screen. And they measure different areas, and they see that these different areas oscillate synchronized. And they measure the coherence and the Granger causality trying to infer the functional structure of these regions. So the point here is that they found, for one monkey, for example, they found that between different pairs of area, the delay, the phase delay between two areas that are synchronized, there is no obvious relation to the Granger causality. So even when the Granger causality says that region A influences region B much more than region B influences region A, we can have that region A lags behind region B. No? This means that, this means that in these red regions, they have the Granger causality points, for example, from 2 to 1, but the 1 is leads the 2. So exactly what we see in anticipated synchronization regime. And they also see something that's like the delayed synchronization regime, for example, 5 to 1. 5 Granger causes 1, but 1 leads the oscillation of 5. 1 has a peak before 5. And that's what we want to compare to our results, because in our case, as we know the structural motif, we know the flux of the direction of information. We know that the causality goes from the master to the slave, but in the anticipated synchronization regime, the slave leads the master. So we know in our case, and we want to compare with them, but okay, we can do Granger causality measures to exactly compare with their measure, because they don't know.
You said that the slave is, leading, of course, but like causality, that it has given information to the master?
No, that's the point. The master gives information to the slave. Always. And that's what they measure here. They measure, for example, that 2 send information to 1, but they don't know the structure. They just say, okay, with Granger causality measures, it seems that 2 send information to 1. Imagine that this Granger causality is infer the reality, is saying the reality. So we have that 2 is sending information to 1, like 2 is the master and 1 is the slave, but we have that 1 leads the master.
Yeah, but I don't see how, because when you have 2, it's easy, right? You build the thing and you know which the master and which the slave. But there you have like 5 different groups. Okay. So who is the master and the slave in that case? That's impossible to say, because that's not the picture, right? Okay,
it's impossible to say, but they say they do Granger causality measure, and they say that looking for Granger causality, it seems that one region really influences the other. That's what they found.
They take pairs of regions. They analyze pair by pair the region, and we find that sometimes the region causality is positive, but the phase is negative.
Yeah, but inside the diagram with 6 different nodes, it's, I don't know, that's because, you can really, I don't know. I don't know how to fit that. I know what Granger causality is measuring. It's not measuring causality, it's measuring a specific definition of causality. Yeah. So how this is translated into the whole picture with the links and everything there. So, but I don't see how to fit all that.
The point here is that until this paper, people used to think about if we have someone leading another one, they think that the causal relation is from the one which is leading to the other. Okay? And here they show that sometimes this is not what happened. It's just that. They show that with Granger causality, sometimes you have the direction of causality and the delay in opposite directions.
Yeah, but then better than okay.
Okay, maybe they are not even connected. These 2 regions with a Granger causality, but they have this result that the phase delay can be different of the direction, and we are showing that in our case that is very special because we really know the connectivity. We have that always the Granger causality points out from the master to the slave, even if we have the anticipated synchronization case. So we are showing that if this is happening here, this can be explained by anticipated synchronization. Maybe this is not what is happening here, because maybe they are not even connected. Okay. I have time.
So for those of us who do not know, what is Granger causality?
It's a measure that if you have two signals, you can try to predict, knowing one of the regions, you're trying to see who is better to predict the other. So if you have x and y, and you consider some points of x, it's easier to predict what's going to happen with y, or the opposite is better. So it's who is influenced, who in a very linear case.
But do you need to know the dynamics to avoid that, or you avoid from the time series?
Just the time series.
And you assume that the series are linearly related. That's the assumption.
So,
and if they are not, they don't give a good prediction. And to measure that, it usually uses correlation or mutual information.
You go one step further of correlation, because now you know the flux of information.
Yeah, but then I need to go in Granger causality, use something like correlation, or use mutual information, or what sort of a statistical measure here?
the mutual information does not give the direction.
Yeah, that's what I mean. So what do you use for Granger causality? What sort of statistical technique you measure? The correlation? What do you measure?
No, it's
Transfer entropy, maybe? Do you use transfer entropy?
no, they didn't use transfer entropy.
Something different, okay?
In 2004, Granger causality was very good because people just used coherence. Now there are a lot of different indexes to measure that.
But up to now, most of the people working in medical time series, they use Granger causality. I think they don't know very well, as me probably, how it works, but they only use that.
But there must be a formula or what the time series of that.
There is
something with 2 series and
yeah, you do. It comes from stochastic process.
Yeah, sorry.
So you are not?
No.
Okay.
No. Because yes, I'm gonna change a little bit. So.
Okay, no, my question is, what is changing in the system? Because, I mean, you have shown a lot of plots, there is some cases where you anticipate, or when sometimes when you delay, but this is due to what? Because I was expecting that you have some internal characteristic time in the dynamics, and when this is larger than the other, then you anticipate, and in the other cases you...
The inhibition.
What?
The inhibition? When...
Yeah, you're changing the conductance, right? And I suppose that this is related to some internal time in the different populations, right? So, my question is, what is changing? I mean, what determines whether you are anticipating or delaying?
In my model or in experiments?
In your model.
The inhibition is somehow helping that the slave population, everybody spikes before the muscles.
By doing what?
Sending current? No?
No, but what, I mean, what, from the physical point of view, what is changing? So the internal time is changing what? I mean, because it should be a competition between internal time and propagation time and things like that. I mean, that's probably the whole thing, right?
Okay.
So I kind of...
In the 3 neurons case, maybe the threshold, no? Something like that. That's what it is. Because if we send inhibition and the model is a resonator, this inhibition is facilitating the spike. So the inhibition is somehow helping the slave to spike before all the signal of the master arrive. But in the, I didn't get your
from the physical point of view, what is really changing? Facilitated by putting the time scale of the same order and being the same. This is the
I don't know.
Well, actually, the explanation we found before with Raúl is that it reduces the threshold. The feedback, in that case, reduces the threshold such that the slave spikes faster. And this is the same case. Inhibition, what does reduce the threshold in the slave population such that it can respond before or faster.
But changing the conductance, you can have the three regimes. So even if you continuously reduce the threshold, you can switch from one to the other, right? So
in some cases, you have a regime of inhibitory values for which you have anticipated synchronization, and out of that regime you can have delayed synchronization. That is true.
Then,
well, for a small one,
you haven't looked into characteristic time for the dynamics, just changing the conductance and things like that.
No.
That probably.
Maybe we can talk, because as there is a lot of parameters, it's quite difficult to say what ones are good to change. Like which ones are important for physical understanding, for example, because you cannot access directly. If I change the synaptic decay, for example, in the 3 neuron case, I can understand a little bit what's happening, but in the population,
yeah, you can do the population and characterize how the characteristic time of the spiking changes parameters, right? You can do it numerically. So you know.
Yes, but I can do
that is changing in this direction. And what is happening is that the two characteristic times are becoming similar or they're becoming more different.
But but as I have a lot of for which ones are good to investigate, because it's quite unreal to do for all of them. No?
No, not for all of them, it's for one.
Okay. So to finish this part, last year appeared another paper with different experimental setup that they see again these discrepancies between the Granger causality influence and the time delay. So in this situation, the posterior parietal cortex is acting like the master, and Granger causes the prefrontal cortex. But the prefrontal cortex seems to lead the master in 2 to 6 milliseconds. So they oscillate with 17 Hz, and always the prefrontal cortex is spiking before the posterior parietal. And they also use another kind of causality measure, and they see the same result. So the idea is try to get the data to compare to us and do different kinds of causality analysis to make sure that's not a problem of the Granger or something like that.
We have the data already.
So the next part is quite different that I was showing to you, is more based on neuroscience results, is trying to putting together the ideas of anticipation and spike time independent plasticity. So what is it? People have seen that the strength of synapse between neurons can change depending of the order of the spikes of the neuron. So imagine if I have a neuron that sends a synapse to the other, like in the master and slave, and in this graph they measure how the strength of the synapses, so the conductance of the synapse, can increase or decrease depending on the time difference between these two spikes. So here, if you have that the master spike first and then the slave, we have that this synaptic strength increase. So we call it long-term potentiation. So they see that depending on the time difference here, the synaptic the potentiation is larger or not. And the same for the long-term depression that happens if the slave is spiking before the master. So we say that it's not a causal relation because they are not thinking about anticipation. So we have that if the slave, even if I make the slave spike, not the master, I make the slave spike before the master, we can have LTD, that's long-term depression, and the strength of the synapse decrease. So based on that, we can do a relation of what we have in delayed synchronized regimes and in anticipated regimes. So here, it's going to happen LTD when we have anticipation, and it's going to happen LTP when we have delayed synchronized regime. So if we apply these rules that can be described by these sets of equations that fit this curve, what happened to our populations of neurons? So what we see is that for the 3 neuron case, that we have these bigger regions of anticipations is below the blue region. We can imagine that if we are here and we have this is the oscillatory conductance, the synapse that's going to change. Okay, so here in this region we have that the slave spike before the master. So by STDP rules, we have that these strands decrease. So these synapses go to a 0 value. You can think about that. And in these blue regions, we have the opposite. Because we are having that the master spike and after that the slave spike, and we have that this conductance decrease, this conductance increase. Okay, so this is not very interesting because if we apply STDP rules here, we have just simple. If we start in the red region, they go to 0 or to our lower boundary that we can put by hand because biologically the synapse will not disappear. And if we are in the blue region, the conductance go to the upper boundary, so we can imagine that it achieves its maximum. Otherwise, if we consider the 3 large scale networks, we have a different situation because we have in this region that the red regime is above the blue, so anticipation here is above the delayed synchronization. So we can imagine that if we are here in this red region, we're gonna have anticipated situation, gonna have LTD, so depression, so the conductance will decrease. But if we are in the blue region, we are gonna have a potentiation, the synapse, the conductance will increase, and we have something that will be equilibrated here. So we apply plasticity rules. In this case, it's not that direct because we have a lot of synapses and not just one. It's not exactly walking this line. But what we see is that our results of what happens to the system, so the system goes to a steady state synchronized regime, like it's close to near 0 like synchronization, and the weight distribution of the synaptic weights. Now just applying the equation, just applying the STDP rules, the system alone organizes itself to a distribution like that, exponential and unimodal, that almost everybody is 0 and the other ones decay exponentially, which is very similar to experimental results in different regions, in different cortex regions. So here they do not have the 0 value because if the synapse is 0, they cannot measure in the experiments. They infer how many synapses is 0 here, and usually is a high number like here. But the rest of the graph is very similar to what we found. On the other hand, the other typical numerical results that people do without anticipation, if we apply one kind of plasticity, we have a bimodal distribution, so we have the second peak here that is not seen in real networks, in experiments. Or we have an unimodal distribution that is not around 0. And this is not, again, what they see in experiments. So maybe anticipation is regulating the system, that it's not necessary anymore to say all the upper limits of synapse, conductance of the synapse is put by hand. It's not necessary to put the boundaries by hand. So let's see.
Questions, comments?
How many cycles, how many spikes do real neurons need to make a noticeable depression or potentiation? It's just a single spike is enough to make...
No, no.
What is the other magnitude?
100. They call tectonic spikes because there's really a, in the slice, there's really a protocol that you need to do, like sending 10 spikes with distance of the 10 next one of 2 seconds, and it's quite specific to appear the. But in these first experiments, now they are trying to looking for that in a lot of different cases, and it's more flexible.
Yes. David?
Yes, so in your model, I didn't understand, the conductance has changed because you have an extra term or because they're different correlate? I
changed the sorry, in the plasticity case or in the
first case?
No, in the first case I changed by hand. I see, oh, if the conductance is this value, what happened? And I see what happened. And then if this conductance has this value, what happened? And then I do the simulation again.
So experimentally, is it possible to know what is the typical size of these conductance populations?
In the interneuron case that I show experimental setup, they change because it was a hybrid setup, and they can change here. They can change this inhibition because this is a simulation. In an experiment that is completely biological, we can use neuromodulators, but we cannot change like 1 or 2 Siemens. We just change, we put the neuromodulator and increase or decrease. It's not very controlled.
How sensitive are your results with respect to whether you are in a spiking or bursting version?
We like for the populations that we have, as we have neuronal variability with these constants. These constants are saying the proportion of regular spike and burst. So I can have a smooth curve that if I'm going to change A, so if I'm going to change this proportion of bursting and regular spike, the anticipation is getting smaller. For the 3-neuron case, I didn't find for a burst model, anticipation a burst model. It doesn't mean that do not exist, but it's more difficult to find.
Thanks. I wonder how big the role of the symmetry between the different corresponding conductance values is. For example, in the tri-neuron model, these 2 G8 figures, and also within the considered populations. If you,
I don't understand. Sorry.
I guess for anticipation in any case, you need some kind of symmetry between or within your system, your considered system. So with the tri-neuron model, you have these 2 conductance values G8. So I guess they have to be symmetric to some degree. And also I wonder about the diversity of the neurons within these considered populations. So you have a couple of populations, how similar do they have to be? Or how similar are they actually in reality?
Okay, in the 3-neuron case, they are really identical. Identical neurons. Actually, I didn't test how I can change. I tried to put different external currents in both of them and see for how long, but it's quite difficult numerical to access that. For the 3-neuron populations, I start with this model in which the master is very different to the slave because the slave is just oscillatory. So if I put this connection 0, the slave oscillates with high frequency than the master. So they are similar because I'm doing like using the same Scratch neural model with parameters that are similar, but they are not identical. So in this case, I have a...
Okay, so you use some narrow distribution basically for the conductance values within the population.
No, the conductance is constant for all.
Right.
Yes, but I believe that inside the population, if I change a little bit the conductance, there's no problem. The points that alone the population is oscillates similar. If this population alone oscillates with similar to this population, when I couple them, I can find a phase lock regime, and then I can look in for anticipation.
Right. So in the last part, you have presented, plasticity with this motif leading to synchronization. Right now, it was fine.
Okay.
The picture. So there are other alternatives like the 3-motif for zero-lag synchronization, right? Where you have basically the interneuron should also be connected to the master. So that's the other proposal by Ingo, by Claudio, right? So
Okay.
that's a different mechanism because there you have plasticity, but also leads to zero-lag synchronization. My question is, what are the advantages of this versus the other, or when do you expect to have this and the other? Because there's different ways to reach the same final state, right? It's a synchronization with zero lag.
Okay, but the point is that in their model, you have zero lag. Here I can have phase lag.
With plasticity, it's also zero lag, or I misunderstood.
No, not necessary. Like here in this region, if we have something around here, they go to near zero lag. But if we have here, they go to a state that
the case where you have, for the case when you have zero lag synchronization, what are the advantages for this versus the other?
Okay,
or when do you expect to see these motifs? And
I can defend that both things occur, like both motifs. We know that some cortical regions are structurally connected unidirectional, and some are structurally connected bidirectional. So if we have two regions that I'm sure that are unidirectional structurally, I'm expected that it happens something like that, and maybe I can see anticipation. If they are bidirectional, I cannot expect that.
But from the dynamical point of view, there is no difference. So the two mechanisms are robust.
Okay.
With respect to the diversity, I don't know.
Maybe the brain wants zero lag in no matter what's the motive. Both, no, really. It's good if you have two mechanisms that go to zero lag, no?
No, but my question is why, how do you choose one or the other? What are the advantages?
No, I chose this one because it's the one I was studying.
Can you briefly explain the other two learning rules, the NSTDP and the WSTDP?
Okay.
Different about them.
Yes, the point is here. Like in these equations, here I pass very fast because I don't want to go to details, but the point is that we can have that we call additive plasticity rules, and here multiplicative plasticity rules because this term. So we can have, this is for LTP and this is for LTD. We can have that both equations do not depend on the old value of the conductance. So the increase is always additive. It doesn't depend on the value that you had in the beginning. Or we can have that both of them depend on the value you have. So I can put the double here. So both of the LTP and LTD depend on that. So this is, if I use double here and here, I will have this and STDP. I will have the double STDP. If I do not use double STDP in neither of the equations, I will have this additive STDP. But some recent papers are appealing that if we use this how can I say, this mixed state, so it's more similar to what we see in these results, because for decreasing, it really depends on the value that you have. But for increasing, no. And then if I use these results, I have this curve. But people even when people use these hybrids, they do not have this distribution, because this distribution appears because of dissipation.
So in arbitrary network it doesn't appear?
Yes.
Okay.
Another question? Just one comment, since Fernanda found this paper by Steven Bressler about the PNAS paper 2004 about this relation causality with a positive value and negative phase, we contacted them, telling our story, and he seems to be very, very interested now. Actually, he sent us already some data from the monkeys, because they didn't expect at all that the local change in inhibition could yield this anticipated synchronization mechanism that they feel is there. They have written that in many papers, but never explained. They just put it like a small letter, because they couldn't explain why would that happen. And now he seems to be very excited with our research, and we are trying to see if we can match our model with their experiment. So I think it might be a very nice end for the story, at least for the moment. Okay, well,